Welcome to Study Loop.
In this problem, we're given the shown equation, which describes a gas where we have a pressure, a volume, and a temperature of the gas, and we're told that they satisfy this relationship. And we want to regard V as a function of the temperature and the pressure. And what we're going to do is we're going to calculate the partial derivative dV dt. And what we can do is calculate this by implicitly differentiating the relationship above, since it's an equality. That's also going to set an equality between the various partial derivatives. So what we're going to do that's a little bit different from other problems in the set that we've done is we're first going to take the log of the governing equation. So we can rewrite the governing equation as saying that P times V minus P times e to the stuff that's up there divided by RT is equal to 1. And we can take the log of everything. Remember that the log of a product is equal to the sum of the logs. And remember that the log of 1 is 0. So this is going to give us some function that's always equal to 0. So if we take the log of that, I'm going to call the resulting equation G. And it's going to be equal to the log of P plus the log of V minus B, which we're assuming is positive, plus A over RVT minus log of R minus log T. And this is always equal to 0. And so now if we implicitly differentiate, we know that dG dt is going to be equal to partial G partial T plus partial G partial V times the chain rule application partial V partial T. And so right away that tells us that dV dt, or partial V partial T, is going to be equal to negative dG dt divided by dG dV. So if we calculate these two things, we'll be done. So first, let's do the easier one first. I think that's probably partial G partial T. So if we go through and we remember this is just the terms that rely explicitly on T, that's going to be this one, which has a T in the denominator, and this one, which is obviously the log of T. And so this is going to be equal to minus 1 over T minus A over RV T squared. And we can group terms and calculate this as negative 1 over RT times R plus A over TV. So there's 1. Now we can calculate the other partial derivative. This is partial G over partial V. And so if we look at terms that have an explicit factor of V, there's this one and there's this one. So that is going to give us a 1 over V minus B minus A over R V squared T. And again, we can pull out a common term of 1 over RT, and we can write this whole thing as RT over V minus B minus A over V squared. So there's the other one, and now to calculate the actual term, we just substitute into this expression. So the negative sign here knocks out this negative sign. Our 1 over RT is going to calculate our 1 over RT, and this suggests that dV dt, I need to go back and correct this. This factor of little t is actually a big T because we're worrying about gases, not time evolution. So dV dt is equal to R plus A over TV, all divided by RT over V minus B minus A over V squared. And that is exactly what we were asked to prove.